Oh, gosh, Bugger. Bugger, come here. Come here. Where did I get the name Bug? There's a book called Ender's Game, and in Ender's Game, the aliens, it's a sci-fi book, and the aliens are called buggers. And so that's part of the reason. And the other thing is, my family has always said about something that's cute, like say, oh, that's a cute little bugger. And so he's a cute little bugger, so that's why I named him Bugger. Mm-hmm. Kind of looks like he's doing the Macarena. Yeah, you're funny. Okay, bye-bye. I gotta teach. All right. I guess I will start. Hello, everyone. Happy Friday. You know, the year seemed like it was going by really fast at first, and then last week and this week have seemed really slow to me. Like second triad has just really slowed down. Okay. So let me do a little review of what we learned about last time. Okay. Last time we learned about a couple of different forms of energy. Okay, the first type we learned about was kinetic energy, which is denoted by 1/2 mv squared. Okay. And that's the energy of motion. It's the energy of motion because it has velocity in it. Okay, the faster you go, the more kinetic energy you have. And then we learned about potential energies, which are energies that don't depend on how fast you're going. They depend on where you are or how you're configured. Okay, and so the one that we looked at last time was gravitational potential energy, MGY. And then another form of energy that we discussed, but we're not really going to go too deeply into it, but it is very important, is heat or thermal energy, which is typically denoted by Q. The total mechanical energy of an object is equal to its kinetic energy plus its potential energy. Now, there could be so this is all the different forms of potential energy. So we talked a little bit last time about how there's a chemical potential energy, electrical potential energy, different types of potential energy. So that's all of those added together. That's why I didn't put a subscript G there. And then we went on to learn the law of conservation. Of energy. And so, as I said last time, at least I think I said it last time, that conservation laws are very common in the sciences. So a conservation law means that the total amount of something is not changing as time goes on. And so some of the conservation laws that you probably encountered in chemistry class are conservation of mass in chemical reactions, and conservation of electric charge. Okay, conservation of energy. The mathematical statement of it is that this total amount of energy that the universe starts out with is equal to the final amount of energy that the universe has. Okay. The law of conservation of energy is strictly true only for the universe as a whole. Okay, because if you have a subsystem of the universe, so not the entire universe, but just a part, energy can flow into that system, that subsystem, or it can flow out of that subsystem. Okay, so if we think about the Earth, energy is not conserved for the Earth. Where is a lot of the Earth's energy coming from? Can anyone tell me? Type it in the chat if you know. But if you have an isolated system, energy cannot be created or destroyed. Only transformed or transferred. Excellent. Yeah, the sun is a major source of external energy coming into the Earth system. Okay. If we think about the law of conservation of mass, is the law of conservation of mass true for the Earth system? It's actually not, because we are having, meteorites and things hitting the Earth's atmosphere all the time. So the Earth is actually gaining mass as it, as it sweeps out and it collects dust from outer space. The sun actually knocks off molecules from the Earth's outer atmosphere. So there is a flux of mass into and out of the Earth system. There's a flux of energy into and out of the Earth system. So these conservation laws are strictly true only for isolated systems. Okay. I could talk about that stuff for a long time, but I'm not going to. So we're going to learn about a new form of potential energy today. It's called elastic potential energy. Okay? And elastic potential energy is the energy of deformation. So it's the energy that you have, that something has when it is stretched or compressed or made to have a different shape than it naturally has. Okay, if you take a rubber band and you stretch it, it wants to go back to its original state. Okay, so what you've done by stretching a rubber band is you've put elastic potential energy into the rubber band. Okay, if you compress a spring, the spring doesn't want to be compressed. It wants to be at its natural length. You compress it, you're storing elastic potential energy into the spring. Okay, so the symbol for elastic potential energy is U sub E, E for elastic, and it is equal to 1/2 K x squared. So just to remind you what some of these variables are. K is the stiffness of the elastic band. X is the extension or compression. It doesn't really matter because we square it. Okay? So it could be positive or negative. Okay? So this is called elastic potential energy. And we can see that what makes the elastic potential energy larger. To make the elastic potential energy large, you stretch something a lot. It's like if you are firing a bow, an arrow, the further back you pull the string, the more extension the bow has, and so the more elastic potential energy you're putting into the bow, which is then transferred to the kinetic energy of the arrow. Okay. The stiffer something is, the more energy it stores. Okay. If you go to the store and you buy a bow, they have different stiffnesses on the bows. Okay. Some bow, depending on how strong you are, you might want a stiffer bow, because a stiffer bow is going to be able to store more elastic potential energy, which means that the arrow is going to have that much more kinetic energy once you fire the arrow. Okay. So that's elastic potential energy. I want to do just a little aside, and just talk about energy versus force. Okay. One thing that students oftentimes do is they start to, at this point in the school year, they start to mix up energy and force. Okay. So generally speaking, if you're going to be using forces when you are trying to calculate accelerations and when you're trying to do kinematics. Okay, so that's when forces come into play. You would use energy when you have something that is really complicated and you need to do a holistic analysis of what can happen and what can't happen. Okay, so if we think about the roller coaster problem, the shape of the roller coaster was really complicated, and so what we were trying to do was a holistic analysis. We say, okay, the roller coaster starts here and it ends here. Regardless of the details, I don't need to know how much time it takes to get here, but what I need to know is how fast is it going to be going when it gets to that spot. Okay, so you're looking at the system as a whole. Okay, that's when you would want to use energy. So you're looking at it holistically. Okay, and there's a different formula. So for example, there's a gravitational force, which is equal to mass times gravity. There's a gravitational potential energy, which is mgy. Okay? Similarly, there's an elastic force, which is kx. And then there's an elastic potential energy, which is 1/2 kx squared. Okay, so you need to be careful here about, you would never have kx in this equation because that is a force and this is an energy equation. Okay, similarly, you would never say that the elastic force is 1/2 kx squared. Okay, so you would never have 1/2 kx squared in Newton's second law. You would only have kx because Newton's second law is dealing with forces, not energies. So you got to be careful. So that's just a warning. So I'll put an exclamation point for warning. All right. So let's do an example. This example is inspired by Six Flags. If you've been to Six Flags Magic Mountain before, which I have, and it's a lot of fun for about 4 rides, and then I start to get dizzy, and then usually I just sit down for the rest of the day. But those 4 rides are pretty fun. The roller coaster, Goliath, super fun. There's a ride at Six Flags. It's called like Superman or something like that. And the ride basically looks like this. You start out flat, and then you basically just go straight up. And then you come back down. Okay? It's called like Flight of Superman or something like that. Anyone been to Six Flags and they know the name of that ride? You know the one I'm talking about. It just goes like that. Okay, and so we've got a roller coaster cart. Here's the person. Okay, and this roller coaster cart has a mass of 100 kilograms, and it starts out at rest. Okay, now behind this roller coaster cart is a spring which is compressed. Okay, so this spring is going to have a stiffness of 5,000 newtons per meter, and it is compressed by 2 meters. Okay, and so what happens is this spring is storing all of this elastic potential energy. The spring decompresses, and it gives that elastic potential energy to the roller coaster cart, so that the roller coaster cart now has kinetic energy. Then the roller coaster cart starts to climb, and as it climbs, it is exchanging its kinetic energy for gravitational potential energy. Okay? And eventually the roller coaster cart will reach a maximum height. Okay? So this is the initial point, and this is the final point. And what I would like to know is how high does that roller coaster cart go? Okay? So that's part A. There's going to be a part B, but that's part A. So how high can the cart go? All right? So we are going to use conservation of energy. Initial energy equals final energy. The initial energy is the energy of, we have a compressed spring, so we have elastic potential energy. The cart is at rest, so we have no kinetic energy. And furthermore, we're at ground level, so we have no gravitational potential energy. So all of the initial energy is elastic potential. So we have 1/2 kx squared. At the final point here, the spring had to decompress in order to get to the final point. So because the spring decompressed, it no longer has elastic potential energy. So we don't have elastic potential energy anymore. Okay. However, we do gain elevation, so we are going to get gravitational potential energy. Okay. And then the roller coaster cart could be moving, so we might have kinetic energy. But here's the thing. If the roller coaster cart is at its highest point, it cannot have speed anymore. Why? Because if it had speed at its highest point, it would still be going upward. Okay? So there is actually no kinetic energy at the final point. So this right here is our master equation. Okay? So now we're going to plug in numbers. We have 1/2 times the stiffness of 5,000 times the compression of 2 meters equals m, which is 100, times g, which is 10, times y. Okay? And so I divide by 1,000 basically, and that gives me the y value. And when I do that, I get y equals 10 meters. Okay? So this roller coaster cart can go up 10 meters before it comes to a stop. So this is probably not as the Superman ride goes up probably 30 meters or more. So this is not as impressive as the Superman ride at Six Flags. Okay? So I'm going to do a part B for this question. How fast is the coaster going when it has an elevation of 4 meters? Okay? Now, I wanted to do part A before we do part B because I didn't know how high the roller coaster cart was going to go. It wouldn't make sense to ask a question like, how fast is the coaster going when it has an elevation of 15 meters? Because it doesn't actually go up 15 meters. So if we tried to solve that problem, we would end up with some kind of a contradiction. So, for example, we might try to take the square root of a negative number. Actually, that is what would happen if I asked the question, how fast is the roller coaster going when it has an elevation of 15 meters? We would get actually an imaginary number for the velocity, which doesn't make any sense. Okay, so I have to give a elevation that's less than the maximum height. So basically, I'm trying to figure out the speed of the roller coaster cart when it's about right there. So we have a y value of 4 meters. Okay, and so just like before, we start off with elastic potential energy. Oops, 1/2 kx squared. And we end up with gravitational potential energy, but not 10 meters of gravitational potential energy, only 4 meters of gravitational potential energy. And because the roller coaster cart is not at its highest point yet, it's still moving, and so therefore it has kinetic energy. All right, so this is our master equation. One thing I want to point out is that for this problem, I had to tell you the mass of the roller coaster cart. Last time, we were doing these problems where mass was in every term of the equation, so mass canceled out, and so therefore it was not necessary to tell you the mass of the roller coaster cart. But once we have elastic potential energy involved, now you need to know the mass of the roller coaster cart, because now this term doesn't have mass. So we have two out of the 3 terms have mass. That's not every term, so we can't cancel out mass. So now the mass is important. So I plug in numbers. 1/2 times a stiffness of 5,000 times a compression of 2 squared, equals mass, which is 100, times gravity, which is 10, times elevation, which is 4, plus 1/2 times the mass, which is 100, times v squared. So that's going to allow me to solve for the velocity. Okay? So let's do that. 25 times 5,000 times 4 minus 10 times 100 times 4 times 2 divided by 100 square root. And so what I get is the velocity at this point is about 11 meters per second. Okay? So again, this is sort of like we're in the process of exchanging kinetic energy for gravitational potential energy. Here at this final point, we've completed the exchange, and it's all gravitational potential energy. All right? Let's do one more example with elastic potential energy. All right? Let's suppose that we have a skater dude or a skater girl. I don't really care. Okay. Oh, we better put a helmet on him. Got to stay safe. Okay. And this skater dude is cruising along at 13 meters per second. Skater dude has a mass of 50 kilograms. Okay, so the skater dude is rolling along. Skater dude goes up a hill. This hill is 3 meters tall. Okay, and I worked out the math for this one already. And 3 meters is not enough to, a 3-meter climb is not enough to bring this skater to a stop. So the skater is still rolling once getting to the top of the hill. And then at the top of the hill, we have a spring waiting for the skater. The spring is initially uncompressed, and it has a stiffness of 750 newtons per meter. Okay? And so what happens is the skater runs into the spring, and the spring slows the skater to a stop. And so the question is, what is the maximum compression of the spring? Okay? So you want to think about energy problems in terms of transfers of energy. What transfers are going on? So we have kinetic energy. We start off with kinetic energy. Skater goes up the hill and loses some of that kinetic energy, but gains gravitational potential energy. So at this point, we have sort of like maybe half and half. I don't know what the ratio is, but we have some kinetic energy, some gravitational potential. Okay? And then we hit the spring, and because we're not changing elevation, we don't lose any gravitational potential energy. What happens is the rest of that kinetic energy becomes elastic potential energy. Okay? So what we have is a transfer of kinetic energy to gravitational potential energy and elastic potential energy. So our conservation of energy equation is going to be a transfer from kinetic energy to gravitational potential energy because we gained elevation, and elastic potential energy because we compressed a spring. Okay? Why isn't there a 1/2 mv squared term in the end? Well, the reason is that I wanted to know what is the maximum compression of the spring. So if the skater has velocity at the point of maximum compression, they're still moving, which means they're still compressing the spring, which means it wasn't maximum compression. Okay? So the kinetic energy is not present at the point of maximum compression. Okay? All right? So now we plug in numbers. We have 1/2 times the mass of the skater is 50 times the speed of the skater is 13 squared. And then they gain elevation, 50 times 10 times 3 plus 1/2 times the stiffness, which is 750 times x squared. So this is an equation we can solve for x with algebra. So I will do that. I'm not going to show the steps. And we get that the spring is going to be compressed about 2.7 meters. Okay? That's the maximum compression. So what if so then I could, I'm not going to do it this time, but I could then ask the question, well, at the moment when the spring is compressed 1 meter, what is the speed of the skater, because if the compression is 1 meter, that's not the maximum compression, so the skater still has velocity. And so in that case, I would need to include a 1/2 mv squared on the right-hand side, because the skater is still compressing, so it still has velocity, and we could solve for the velocity at that moment, okay? So basically the skater slows down while climbing and then slows completely to a stop while compressing the spring. That's what's happening here. All right. So we're going to move on to the second topic of today's lesson, which is energy transfer between systems. Okay? So let's suppose we have a system A, and we have a system B. So the energy of system A is 100 joules, and the energy of system B is 200 joules. So the universe as a whole has 300 joules of energy, because 100 plus 200. Okay? Now system A transfers 70 joules to system B. Okay? What's true about the energies afterwards? So after this transfer, the energy of system A is going to be 30 joules. Why? Because it gave up 70 joules. So it lost those 70 joules, and it doesn't have them anymore. So now it only has 30 joules. System B gained those 70 joules. So now it has 270 joules. Okay? And if we look at the total energy of the universe before the transfer and after the transfer, it's the same, because before the transfer we had 100 plus 200, 300 joules of energy. After the transfer we have 30 plus 270, which is still 300 joules. So the total amount of energy in the universe stayed the same, but it was redistributed from one system to another system. Okay? So we have a special name for this transfer of energy in physics. It is called work. So work is a transfer of energy between systems. So work is a word that you probably use all the time, okay? And it has a certain meaning in your day-to-day life. But when we're talking about physics, work has a very specific meaning, and it means it's a transfer of energy between systems. Okay, so it's an everyday word that has sort of been used by physicists. I don't know why they call it work. It's a bad name, but it has a very specific meaning in physics, which is a transfer of energy between systems. Okay. So let me show you sort of the lingo, the physics lingo. So we could describe this process by saying that A does 70 joules of work on B. So if you do work, you are giving up your own energy and giving it to something else. Okay? That kind of makes sense, right? If you do work, you're expending energy, you're losing energy, and you're putting that energy into something else. You could also say this as B has 70 joules of work done on it, by A. So that's sort of thinking, you can write it as A is the subject of the sentence and B is the object, or you can write it as B is the object and A is the subject, okay? So you can write it both ways. You just got to be careful. A third way you can write it, this would be less common, but it is used occasionally, is to say that B does negative 70 joules of work on A. So these three statements are all equivalent. So if you do negative work, then you're actually taking the energy for yourself. You're a joule thief. Okay? So if I do negative 5 joules of work on you, then I am taking 5 joules of energy for myself. I'm a joule thief. Okay? So that is the lingo. Okay? Thank you. I agree it's a nice pun. So energy is only going to be conserved for an isolated system. Okay? If you have an open system, so for a subsystem of the universe, we have to modify the law of conservation of energy. So it's no longer initial energy equals final energy. It's initial energy plus the work done on the system equals the final energy. Okay? So W is the work done on the system. Okay? So this is really just accounting, is what it is. It's like if your bank account, so using the money analogy, I talked about a money analogy last time, and I talked about how energy is a little bit like money. You could think about work as like a transfer of money between people, okay? So if you start off with 100 joules of energy and you have 5 joules of work done on you, you're going to end up with 105 joules of energy, okay? Just like if you had $100 in your bank account and your grandma gives you $5 for your birthday and you put it in your bank account, you now have $105 in your bank account. Since the universe is infinitely growing, doesn't conservation of mass not apply? So the universe is growing, but it's mass is not being added to the universe. It's just the volume of the universe is increasing. So conservation of mass does still apply. Okay. So let's do a problem using this modified version of conservation of energy. Okay. So what if we have a roller coaster? Okay. And the roller coaster goes downhill. Okay. The mass of the roller coaster cart is 300 kilograms. And the initial velocity of the roller coaster cart is 0. The roller coaster cart starts out with an elevation of 60 meters. Okay? The roller coaster cart goes down and it gets to the bottom, and we want to know what is the speed of the roller coaster cart at the bottom. But there's a catch that makes this different from the previous version. Okay, doing this problem before, you would have said, okay, gravitational potential energy becomes kinetic energy. Okay, but as the coaster descends, the environment does negative 65,000 joules of work on the cart. Okay? So this is actually sort of a more realistic version of the problem because the environment is doing work on the cart. Okay? Think about it. What is the cart doing as it descends? It's moving air molecules out of the way. Okay? Those air molecules, in order to move out of the way, they have to start moving. So as the roller coaster cart descends, it's shoving the air molecules out of the way. So now the air molecules have kinetic energy. That energy had to come from somewhere. It comes from the roller coaster cart. Okay. So if I wanted to say this in the reverse way, I could say the cart does 65,000 joules of work on the environment. Okay. So initial energy plus the work done equals final energy. The initial energy is gravitational potential. So I start out with mgy. The final energy, we lose all the gravitational potential and it gets converted into kinetic. So we end up with 1/2 mv squared. All right. Notice how this term does not have mass in it. We only have 2 terms with mass in it out of 3, so we can't cancel out mass. All right. So, plugging in numbers. 300 times 10 times y, which is 60, plus the work done, minus 65,000, equals, oops, I put a plus, equals, that's an equals, 1/2 times the mass, which is 300, times v squared. So now it's just a simple algebra equation that I will solve. And we get about 28 meters per second. All right? So that's the velocity at the bottom. How does this velocity compare to a situation where the environment does no work on the cart? Type it into the chat if you know. All right, no one is typing into the chat, so I'm just going to say the answer. Because, okay, here we go. Yeah, so air resistance is going to slow the coaster down. So air resistance does negative work on the roller coaster cart, which means that the system is losing energy, so it can't have as much speed at the bottom. Very good. All right, so if we solve this without the work from the environment, we would get a higher final speed. Okay, that's my lesson for today, and I will see you in the Zoom room.